Today we're going to solve polynomial equations which require some factoring before we can solve them. This requires a little bit of background information, so we're going to go over that right now. In a previous video we learned to solve equations like this, and the idea behind this was that we cannot possibly have a product equal to 0 unless one of the factors is 0. So thinking of this as factor A, and this as factor B, if that product is 0, then A must be 0. And if not, then B must be 0. They cannot both be non-zero. It's also possible that for different values of x, they're both equal to 0. And the method that we employed to solve this was we covered up one of the factors, and we concentrated on the other factor. And we said, of course, to get 0 here, you have to have 5 minus 5. And so we said one of the roots, one of the solutions, must be x equals 5. And then we shifted our attention to the other factor and thought of it this way. Maybe we're getting 0 over here because a times b is 0 times something else, so that x minus 2 is equal to 0. Well, that can only be the case if this is 2 minus 2. And so we got our other root, x equals 2. And we also learned to solve things that looked not exactly like that, but more like this. 2x is equal to, or 2x times x minus 4 is equal to 0. And we went after this with the same approach. On each side of the multiplication here that's implied, we looked at the factors, and we said those factors can reveal solutions. So looking at x minus 4 equals 0, we can tell that there must be a 4 here. And that's one of our roots or solutions. They're also called zeros because they create 0 in this product. Then when we looked at the other one, we said, okay, well, if this factor, 2x, is equal to 0, it must be the case that x itself is 0 because 2 times 0 is 0. And this is sometimes harder for students to see, but there's your other root, x equals 0. So we have x equals 0 and x equals 4. Now, this equation that we just solved today is going to be presented to us slightly differently. Today, you're going to see things that aren't pre-factored like this. So let's consider an old problem that I'm sure you've done, which is distribution. How do you distribute 2x into x minus 4? Well, you multiply twice. 2x times x is 2x squared. And 2x times 4 is 8. So we have something like this. And this is the type of problem you're going to see today, which you're not going to be able to solve so well if you can't understand what factors were here in the first place. What did it look like before we distributed? So yes, we're going to go through a process whereby this binomial is factored by pulling out the greatest common factor. And that's what we're going to do today. So let's take a look at this first problem down here. This is not a solving problem. This is quite simply a factoring problem. And the way you go about this is you figure out which one of these factors has a smaller coefficient. Of course, it's 5. And then you ask, well, what kind of numbers go into 5? And 5 is prime. The only thing that goes into 5 is 5. And then you ask, well, will 5 go into 45? So if you need a calculator for this, you go 45 divided by 5, and you come up with 9. Then you'll also notice that both of these terms have z. Okay, so the greatest common factor of 5 and 45 is 5 itself. That's going to come outside like this. And also because these both have at least one factor of z, you can reverse distribute a z out. Now, there will be two things left behind. I call them residual factors, or residue. Your job here is now to figure out 5z times something makes 5z squared. Well, the only thing that this has, that this doesn't, is an extra factor of z. So you put a z here, and then you look at this. 5z times something makes 45z. Oh, well, we already have a z from here, so we won't be needing any more z's to account for that z. All we need is a number that will make 5 multiply to get to 45. And of course, that number is 5 times 9. We did it. We factored it. Okay, it's helpful to always remember that you want to start with a number that's smaller, such as this 6. And you want to know all the numbers that go into 6. See, it turns out in the last problem, we were able to just divide 45 by 5. But you see, 6 doesn't go into 21. And so with a calculator, you can come up with the numbers that divide into 6. There, 1, 2, 3, and 6. And I can show you how that's done for those of you who are maybe not as strong with your number facts. This is how you would figure out the factors of 6. You'd start with something that's equal to about half of 6, like 3. And you'd see that 3 goes into 6 evenly. So now I've got two factors of 6 right here, 2 and 3. And of course 6 is a factor, and 1 is a factor. Now the 1's not going to be very helpful. The next thing you want to do is, starting with the biggest number in this list, try to divide into 21. Will 6 go into 21? And the answer to that is, I think I answered that already. 21 divided by 6, that doesn't go. So you take the next biggest thing on the list, the 3, and you try that. 21 divided by 3. And that one works. So now we know that 3 will divide both of these. With a calculator, you want to divide both of these by 3. And we'll do that in just a minute. But what I learned is that 3 is the greatest common factor of 6 and 21, and 3 can come outside. And see how these also have at least one factor of d? Pull out a d. Okay, that's kind of hard to figure out what to pull out, but it's just as important to figure out what remains behind. So the question we're asking is, 3 times what makes 6? Well, that would be 2. Do we have enough d's here to get to d squared? We do not. We need one more d. Now, 3 times what makes 21? Well, a minute ago we had 21 divided by 3 up here, and it came out to 7. So it turns out 3 times 7 makes 21. But don't put any more d's here, because you only need one in the first place. The d that goes here will come from out here. And it's sometimes worthwhile to check your work. You know, we can always distribute this and see if we get back to where we wanted to be in the first place. 3 times 2 is 6. D times d is d squared. Okay, that compares nicely. And then 3 times 7 is 21. And you will, along with that 21, have a factor of d that comes from here. So that's a way of checking your work, and you don't have to do that every time. But it's available for those who want to make sure they have the right answer. So the answer is this. Okay, let's do a couple more of these. 20x to the third plus 30x squared. What divides both 20 and 30? The fastest way to figure this out is go to the smaller number and come up with all the things that go into 20. And again, what I usually do for that is start with about half of 20 and start dividing. 20 divided by 10. I just learned that 10 and 2 are both factors. 20 divided by 9. 9's not a factor. 20 divided by 8. 8's not a factor. 20 divided by 7. Okay, now some students can skip this step because they know all the things that go into 20. But other students are going to want to know that you can use a calculator to, oh, here we got another one, 5 and 4. So I know the factors of 20. They are 1, 2, 4, 5, 10, and 20. And by the way, this process I went through on the calculator, You don't really have to start with half of 20, like 10. You can start with the square root of 20. So this makes it go faster, and it actually works. Take square root of 20, which is about 4.4. That really means that all I needed to do was take 20 and divide it by 4, by 3, by 2, and by 1, and I would have come up with all of these factors. Okay, now our job is find the number in the list, the biggest number that divides into 30, because all these numbers divide into 20. We want to get the biggest one that also divides 30. Okay, 20 doesn't go into 30. If you go 30 divided by 20 on a calculator, you'll get 1.5. 30 divided by 20. It's 1.5. So that's not helpful. But I think you can probably see, even without a calculator, that 30 does divide by 10. It goes 3 times. So 30 divided by 10 is 3, and that's going to get us started. 10's the greatest common factor of 20 and 30. 10 comes outside. And this time I do something you haven't seen yet today, which is there are 3 factors of x here. X, x, x. There's 2 factors of x here. So this has more x factors than this, but they both have at least 2, and that means you can take x squared out. So that's the greatest common factor with variables that'll come out of each term of the binomial. Now go back and figure 10 times what makes 20? Why, that's 2. Okay? Now we're trying to make x cubed, and I only have x squared here. You will need one more x. Whereas over here, I'm trying to get to x squared. All the x's I need will come from here, and I won't need any additional x's here. 10 times 3 is 30. So I put a 3 there, and I'm done. Okay, this one's interesting. 5 and 2, which one's smaller? 2. Well, what are the factors of 2? Well, just 1 and 2. 2 goes into 2, of course, but does 2 go into 5? No. So it turns out the greatest common factor of 5 and 2 is 1, and that's all you can pull to the outside. But you can pull a lot of n factors. This has got 6 factors. This has 5. You should pull 5 factors of n outside here. And then for the rebuilding, I need a 5 here because 1 times 5 is 5. I need an additional n so that I have 1, 2, 3, 4, 5, 6 factors of n. And then over here, all I need is a 2. Now, I mentioned today that we were going to be solving some equations. Here's an equation that we need to solve. And it's going to use some of the techniques we've seen so far today. It's not factored. So it's nothing like the one we started with here today, where we could just find the answers of 2 and 5 by thinking about how to make 0. You can't do that with this problem. Not yet. But once we factor it, it'll be pretty much the same thing. Okay. There is a 1 in front of this p, of course. It's important to know. And the greatest common factor of 4 and 1 is just 1. So to the outside comes nothing but a 1, and maybe a p factor, because they both have p factors. This has only 1, and that's all you can pull out. So you go 1p, and then you go back and rebuild, thinking about, if I distributed with p, 1p, how could I get to 4p squared? Well, you need 4, because 1 times 4 is 4, and you would need another p. And then 1p times 1 makes 1p. So now that this is factored, we're going to go get the easy answer first. We're going to have our ice cream before our mashed potatoes. We're going to cover up this whole thing and just ask, if 1 times p equals 0, doesn't this have to be 0? Yeah. That's one of your roots or solutions to this problem. P equals 0. Now for the hard one. If 4p minus 1 equals 0, what goes here? And the answer is, it's a fraction. It's not going to be a number like 2 or 3. The way you find that fraction is you just solve 4p minus 1 equals 0, like in first semester algebra. Your goal is to get to here where p is all alone. You're going to start by adding 1 to both sides. That's going to cancel. You're going to get 4p equals 1. and then you're going to have to divide both sides by 4. And that is where the fraction 1/4 comes from, and that's the other answer to the problem. By the way, if you'd like a shortcut to get that second answer, the shortcut is out there. Take the number that doesn't have the p on it, which is -1. Take the opposite of that. Okay, now we're at +1. Now divide by the number that is multiplying the p. And you don't have to go through all those steps of solving that equation. Okay, let's get another one done here. 18q minus 2 squared equals 0. This is the smaller of the two coefficients. Does 2 go into 18? It does. Well, then 2 is greatest common factor. So out comes a 2, and out comes, yes, they both have at least one factor of q. So outside I have 2q. Now 2 times what makes 18? 2 times 9. And 2 times what makes 2? 1. Do we need any more q's? Well, not here. This q times this 9 and this 2 will make your 18q. I only had one q here, and so I don't need an additional one inside. It came from here. But to get -2q squared like this, you'll have to go 2 times q times -1 times another q. Now, to solve this, I'll cover this one up first. If 2 times q equals 0, it must be the case that q equals 0. Okay, 2 times 0 is 0. So there's one of your answers. How about solving this one? Is this one easy? I think it's easy if you decide that that 1 is optional, because now it looks like this. 9 minus q equals 0. 9 minus 9 makes 0. So q equals 9 is your other answer. Solving this one. 3n squared equals 9n. Well, we're relying on these things being equal to 0, and if they're not equal to 0, you're going to have to do something like subtract n from, or 9n from both sides. That will make the 0 that we want on the right. Now the left side looks like 3n squared minus 9n. The smaller of these numbers is 3, so you have to divide 3 out of both of them, like this. Divide out a 3. Also take out 1n, because this has an n and this has 2. The smaller number of n's is the one that is the number that can come out. So 3 times what makes 3? 1. Do we have enough n's here to get to n squared? No, we need one more n. And then over here, all you need is a number 3, because 3 times 3 makes 9. You don't need more, additional n's here. Okay, let's solve this. If 3n equals 0, then n is 0. So that's one of the answers. If if 1n minus 3 equals 0, well, that's equivalent to saying n minus 3 equals 0. And that means this must be 3 minus 3. So n equals 3 is your other answer. Oh, we're running up close to 20 minutes here, so I'm going to skip that problem. I'll start it for you, actually. You want to have 0 on one side or the other. The easiest place to get 0 is on the left. So add 28r to both sides. And the equation now looks like 0 equals 4r squared plus 28r. And then I'll show you the next step, and then I'll let you finish this one. These both divide by 1 and 2 and 4. The smaller of these numbers is actually the greatest common factor of 4 and 28. And they both have r, at least one r. So you take 4r out, and you're going to be left with 1r plus 7. And the answers are going to be 0 here and -7 there. Okay, does this equation have any real roots? It does not. Why? You can't make these things into 0. Because if you square a number, any number, the answer is never negative. Negative 5 squared is positive 25. So it turned out the smallest value this expression can have is 3, since x squared is always 0 or larger. So you don't get 0 over here because of this expression. The same thing can be said for this one. This expression is never smaller than 1. So the answer is no. No real solutions. Okay, finally, find a polynomial that has 1 and 2 and 3 as roots. Well, all you have to do is think in terms of, you would need, if this is a root, you would need a factor like x minus 1. So these are all good. If 2 is a factor, you would need, or if 2 is a root, you would need a factor like x minus 2. Well, these all have x minus 2. Well, if 3 is a root, you would need a factor of x minus 3, and they all have x minus 3. So unless I'm reading this wrong, I think that all 4 of these polynomials have roots at 1 and 2 and 3. Okay, well, we're done here. Hope you enjoyed this. My name's Eric. Have a good day.